Okay, so we start the webinar. Good morning, everyone. Thank you for joining today's meeting. Today we will present the extended components developed within the SecureGas project. So firstly, following the welcome note from the project coordinator Clemente Fuggini, we will have Rossana Grimaldi from Leonardo, who will provide us with a short introduction to the extended components, explaining in short what they are, how they were developed in the project, and how they are used in the project. And then the partners responsible for the business cases implementation will explain in more detail how the extended components are used in the respective business cases. So just before the Clemente starts, a technical note. We have foreseen also some time for questions and answers. So you can either ask questions or provide your comments that you have after each presentation made by each presenter, or you can also wait until the end of the webinar if you have some more general comments or questions. But please ask all your questions in the chat here on the bottom of the screen. So with this short introduction, I invite Clemente for the welcome note. Thank you.
Okay, thank you very much, Carolina, and thank you to all for joining us today in this webinar of SecureGas project. I'm really pleased to see stakeholders external to the consortium partners joining us, and that's the purpose of our today's workshop. Only a few words from my side. First of all, I'm Clemente Fuggini. I'm the coordinator of the SecureGas project, and I work for RINA, an Italian consulting, engineering, testing, inspection, and certification company. SecureGas is now entering into its second half of activities. So more and more the products that SecureGas intend to provide to the market are in development phase and are going to be tested and validated into three relevant business cases owned by end user partners. With end user, I mean energy company, infrastructure, gas infrastructure operator, both on the transmission side and in distribution side. So that to cover ideally an entire value chain from the production, so from the extraction production to the domestic demand of gas supply, with the idea of providing then solution and relevant cases to be replicated afterwards by the market. So as said, the extended components are a very fundamental element of SecureGas strategy, since they do represent our products developed by technical provider and solution provider within the consortium. They are at the moment quite mature in terms of technology readiness, but we need, as said, to test and validate them into relevant business cases, so installation plants, in order to show to the stakeholders and to the market their potential use and usability for commercial and industrial purposes. I think that this webinar is a very, very good introduction to the topic, and I'm sure there will be others in the future where we can show to you the development done and let you understand the level of maturity of what we have developed and we are going to deliver to the market. So with these few words, that's all from my side. I would like to pass the floor to the presenter of the webinar, and in particular now to Rossana Grimaldi from Leonardo, who is the technical manager of the project as well. So thank you very much, and I hope you will enjoy these 45 minutes.
Thank you, Clemente. Good morning, everyone. Then I share my screen for the presentation. Okay, can you see the screen?
Yes, we can see the screen.
Okay. Good morning. In this presentation, we try to understand what are the extended components and why they are so important for SecureGas project. SecureGas project is a path that started on May 19, but we didn't start by scratch because we start with the components. Components are products and technologies brought into the project by qualified partners. In the last year, components have been extended, that is improved and adapted to address SecureGas objectives. As you know, the main SecureGas objective is to improve the protection and resilience of gas-critical infrastructure. This general objective has been made concrete through requirements, operational requirements and technical requirements coming from our end user. They are EWPMS from Greece, Cybercard from Lithuania and ENI from Italy. But also external to the consortium stakeholder provided us additional requirements during workshop held last year. Extended components are still not SecureGas solution. Extended components have to interoperate with each other to build an advanced and innovative solution. SecureGas solution has been customized, integrated and implemented on the gas infrastructure of the end user. In this moment, the consortium is involved in the preparation of the business case that will start the first month of the next year. Now, let's have a quick round trip on extended components. They are 13 components, so we have no time to deep each component, but I will try to give you a glimpse on the main function provided by the components that is exploited by SecureGas project. Let's start with drones. We have two kinds of drones. UAV for patrolling is an ultra-lightweight UAV, smart, energy-efficient ground station, cost-effective, for scheduled and on-demand unattended surveillance and asset management. Another UAV. This UAV is provided by EWPMS and will be tested in the ENI infrastructure. The second UAV is a system equipped with special camera for asset management and surveillance of pipelines in order to detect potential threats starting from leakages up to intrusion and third-party interference. This drone is provided by Ital Drone and will be tested in the underground infrastructure. Distributed acoustic sensing is an extended component aimed at leak detection, able to convert a fiber optic cable led along the pipeline into an array of virtual microphones. It is provided by ELINA and tested in ENI infrastructure. Biometrics and video analytics aims detection, tracking, recognition and identification of people, vehicles and objects in a wide monitored area based on convolutional neural networks and machine learning algorithms. It is provided by IDMG and tested in EWPMS infrastructure. Industrial pumps aims to the protection of the industrial network, provide OT asset discovery and visibility, detection of known and unknown OT threats and anomalies, as well as deviation from operational restrictions. It is provided by Elbit and tested in amber grid infrastructure. Geo-hazard assessment is a tool to assess landslide stability along pipeline routes, resulting to past historical statistical engineering and is supported risk parameterization. It is provided by RINA and tested in ENI infrastructure. Blockchain for data transmission integrity use the KSI blockchain technology for building integrity verification mechanisms to protect the communications among SecureGas modules. It is provided by GuideTime and tested in amber grid infrastructure. Gas network modeling and simulation develops a gas network simulation software that will enable the user to predict the gas supply situation under various operational conditions. The simulation also allows quantifying and ranking the risks and identify recovery models. It is provided by Fraunhofer and tested in amber grid infrastructure. This is the last group of extended components. Cyber-physical correlator combines heterogeneous data to detect and forecast potential physical, cyber and cyber-physical threats, as well as to propose mitigation actions based on machine learning and analytics techniques. It is provided by Wings and tested in the EWPMS infrastructure. Wings platforms facilitates data aggregation, management and utilization, provides user interfaces, visualization tools and communication features. It will be tested in EWPMS infrastructure. Joint cyber-physical risk and resilience modeling and management performs risk assessment, quantifying and ranking the importance of network elements and the related risks, and supports operators before, during, and after an incident occurrence. It is provided by ExosGAT and tested in EWPMS infrastructure. Safety and security platform for gas-critical infrastructures manages all the information coming from the systems operating the critical infrastructure, both provided by end user and technical partners, allowing situational awareness and decision support thanks to a wide range of both prescriptive or reactive security activities. It is provided by Leonardo and tested in DNI infrastructure. Risk-aware information to the population shares information with the public and civil bodies to see different types of users' identification and relevant data sharing, public, first responders, civil protection, third parties, and so on. Provided by Innov and tested in the EDA-DEPA infrastructure. From extended components to SecureGas solution. Each extended component provides a set of functions and services. You have just seen in my quick round trip how many functions and services, how many different functions are provided by the component. Each of them aims at protecting and improving the resilience of our infrastructure. Interoperating with each other, the extended components provide a more effective protection than the single component can do. We can say that SecureGas solution is the synergistic exploitation of several extended components interoperating with each other. High-level reference architecture is the framework in which all the extended components take on a specific functional role it can interact effectively, providing more protection than a single component can do. Now we see the SecureGas solution. See the SecureGas solution through the high-level reference architecture. In this slide, you can see that all the components are placed on logical layers. Starting from the bottom, we can see the field layer. In the field layer, we see both components provided by the technical partners of the consortium, but also the system already operating in the gas infrastructure of our end users. These components, on the logical point of view, detect events and alarms. The events and the alarms are correlated by the upper correlation layer. The correlation layer can infer more events or information or alarms that a single component can't do. The situational awareness layer provides situation awareness and decision support, leveraging on the correlated events coming from the lower layer. And finally, the diffusion layer shares the information with the public and civil body. SecureGas business cases. The modularity and the scalability of the SecureGas architecture allows you to exploit selectively only the function and services you need, as will be demonstrated by the three business cases. You will see each business case will use only the components, the function it needs, and the SecureGas solution works on the same. That's all on my side. I leave the floor to Clemente to introduce the next sections. Thank you very much for your attention, and goodbye.
Thank you very much, Rossana, for your presentation and the introduction to the extended components. And now I would like to give the floor to the representative of DEPA, who is responsible for the implementation of the first business case of SecureGas in Greece. George, the floor is yours. Thank you.
Thank you very much. Good morning. I'm George from DEPA, and I will be presenting the extended component implementation as it's been happening on the end users of DEPA and EDA in the business case 1 in Greece. So long story short, the technical presentation will follow the components from the technical partners of the BC1 team, and I will be presenting some basic info about the implementation and the characteristics alongside with their installation and use in the end users locations. So quick outline, the use of the extended components in business case 1 can be summarized into the following components and subcomponents in some specific cases, and inside each parenthesis you can see the corresponding partner or partners that they're being working on the installation of that component in the end user space. So following up with each one of these, for the first one will be the presence analytics component and the video analytics component used by the ENOV and GAP, following up for the sorry, why are the slides moving forward? Okay, do you see the components diagram slide?
Yes, we can see that.
Okay, sorry for that, but it got stuck and continued working on. Okay, so in both end user locations, there are some combined component analytics being deployed that focus on the presence of external bodies in the area, video analytics, and environment sensors, which all of them correlate into the WINGS correlator sent to Artemis and the raw components for the incident information. This specific part can be broken down into 3 different installations. So we have deployed some presence analytics to detect individuals in sites and be able to analyze the repeated presence of specific employees in multiple sites or at the same site, or their stay at the specific site for a prolonged period of time. So this also can be combined with analysis on persons and people approaching a specific area of the end user site, and combining it with the continuous scanning from the Wi-Fi spectrum. The presence analytics component can detect suspicious presence. We have implemented this in both end users in broad areas of the perimeter and the perimeter of specific buildings, to identify and detect mobile devices, suspicious human presence, and generate events that will help employees inside having their shifts understand if there is a threat nearby. So in terms of video analytics, we have implemented video analytics components in both sides of mainly in DEPA. And there is a recording video stream for specific vehicles coming in, and we can detect multiple events to send inside the monitoring station, such as loitering persons, abandoned objects, perimeter monitoring, double trip wires, early warnings, or abnormal identification of video or audio. This component was mostly installed in the entry areas of some vehicles for DEPA, and in the entry areas of some people for EDA. It communicates directly to the event correlator of the SecureGas solution, and it will aid also in the authentication and identification of entering vehicles or entering people in specific designated areas. So in the last part of this first component is the environmental sensors gateway. There are some specific spots that have been identified near different zone levels of the industrial systems that will be able to monitor them for environmental measurements. This will include temperature, humidity, noise level, CO concentration, or particles. That will help us understand if there are external threats from materials in terms of safety, sampling of environmental elements that will aid the various shifts inside the end user facilities to understand if something is going off in the in more sensitive areas. And of course, all of this will be communicated back to the central point for the alerting system to acknowledge and disseminate the information. All these sensors are combined, and most of the data is cross-correlated with different inputs. So most of them, we were trying to implement them in specific areas of the end user components to aid the analysis both of the perimeter of designated areas and of people and vehicles coming in and out. So basically, we have a threefold analysis of the area of each end user, depending on the needs and the characteristics of their buildings and site installations. So last but not least, there is the raw component, which connects directly to share this incident data that we've just been analyzing. We implemented this in the central station of each end user, and it will be the main one responsible for analyzing messages, timestamping them, analyzing and operating the communication part for incident location and GPS coordinates, identifying and notifying responsible parties for the incident criticality level and the expected or real casualties inside the site from a more approximation of the situation. Following this component, its main purpose is to provide the information exchange and the quick transfer from the platform incidents and the data communication directly to the headquarters. So, following the next component we should be say a few words about is the Artemis platform from Wings. So here is the Cybercard later. We implemented this in the local server of the end users to combine the data, the aforementioned data that we've mentioned, and forecast some of the parameters for prediction of the future fluctuations in the monitored values inside the facilities. So we will be configuring this particular part of the correlator to raise an alert for resulting classifications of data and incidents according to the needs. DEPA and DEDA have similar needs, but not exactly the same ones. So this will be tailored to the needs of each end user. Currently, both end users have been analyzed, their data, their needs, their risks, and we are in the process of calibrating and integrating the differences. And something happened and I've lost picture. I don't know why. Can you hear me?
Yes, we can hear you. I can see that.
Yes, I lost
something.
Yes, someone did something with the presentation.
Yeah.
Okay.
I think you're back.
Yes, I'm back. Thanks. Okay, so the Artemis platform is implemented like the following example. It will extend the Wings proprietary platform of the Artemis and provide a data brokering system over an API for communicating the end user with the central analyst stations. You can see here the user interface with the monitoring, the visualization of the collected data, as well as the access to the analytics and the functionalities of the SecureGas component. So basically, you can see here an actual implementation that will take place in the end user location to identify the alerting mechanisms from the installed components. And basically, this is what we will see and understand in terms of analysis of events. So last but not least, in terms of Wings and the correlation platform, we also have implemented some devices and commercial off-the-shelf components for sensor data to identify gas concentration, flame detection, and some fence movements inside the facilities. The fence movement is being installed in the perimeter of both end users. Specifically in DEPA covers the entire area of the aggregated fence. And the sensor data for gas and flame are occupying the more critical zones that implement the industrial controllers and the actuators. So basically, this will enable the embedded intelligence to detect violation or abnormal operation inside critical zones or the perimeter and complement the previous components by enabling early warnings in the equipped embedded intelligence. These sensors that monitor the more critical areas are, of course, certified for ATX, and they follow the European standards for durable and resilient installation in more critical zones. So the ATX certification or the XIA is implemented in all necessary locations alongside the end user equipment and installations. And following up, we have the RMG component, which is the one responsible for enhancing the security and the resilience, providing the awareness and the decision support information needed to the end users. So this RMG component has two versions, two different perspectives. The standalone tool that's used to formulate the security breach scenarios and the real-time tool for interconnecting to other SecureGas components to consume the data and allow for dynamic evaluation of the risk level. So this is currently under configuration. both end users will have to input some of their data and their preliminary judgment into the needs of the facilities being monitored. Currently, we are we're in the process of analyzing. We've finished these scenarios, and we are currently analyzing the amount of information that will be sent to the end users. All of them follow the classical event analysis that we mentioned earlier to provide efficient response and fast recovery in cases of disruption. As the end users, we can say that the graphical representation and the clear reference into scales and systems for evaluating any adverse event will aid in escalating or disseminating information quickly and taking the relative actions needed without having to properly analyze everything in very detail and then taking an action, which we find it to be quite useful in terms of time consumption and time efficiency in extreme situations. This is also implemented in the central site areas for both business case owners. There are relevant servers following up the data collection that will implement these components. So with this last one, I'm finishing up with BC1's component installation on the end user locations. Basically, the big picture is that we are having some sensors that they are monitoring different parts of all end user locations, mainly perimeter, environmental, and central zones of interest for critical industrial processes. Every event is followed up by a cross correlation of similar data. Everything is fed into a correlator, and we have some components that each one analyzes the different parts that I've mentioned earlier to generate some alerts using the equipment and the sensors that I mentioned earlier. So I will be happy to answer any questions followed up by any of the comments that you might have. So thank you very much for your time, and let me know if I can be of assistance.
Thank you.
I know the floor to you.
Thank you very much, George, for your presentation. I just had a look in the chat. There is no question at the moment, but maybe there will be some at the end. There were a few comments about the audio. Unfortunately, we, as the administrators of the system, we do not have much influence on how the audio works on the side of the presenters. And now I would like to invite the representative of ENI to present business case 3 and the use of extended components in that case, and then it will be followed by business case 2 in Lithuania. So Simone, the floor is yours. Please use the full screen of the presentation, and thank you very much.
Hi everyone, can you hear me?
Yes, we can hear you.
Okay. So I'm Simone Cesari. I work for ENI in the Innovation Department for Engineering, and I will present the business case 3 that is hosted in ENI infrastructure. Business case 3 addresses the adaptation, customization, deployment, and testing of the architecture of SecureGas, and also the extended component that have been before described by Rosanna. Business case 3 relies on 4 main pillars that we see now on the slides. The first one is the third-party interference and leak detection. Then it relies on the acquiring and georeferencing of any changes thanks to the unmanned vehicles. Then the resilience of the OT-IT network. It means the attack to the resilience from any attack to the control system. And then the forecasting and early warning of landslide that could be induced by rainfall. The 6 main scenarios have been identified based on the previous pillars, and here are described. In scenario A, third-party interference enhancement, the SecureGas architecture will detect and localize any voluntary, malicious or involuntary interference from third party or any leakages. In scenario B, we have the attack to the EWPMS system. EWPMS, we will see later. It is ENI technologies for leak detection and TPI. And here we deal with signal tampering to the EWPMS system. Scenario C deals with the physical event identification. It means when sensor station is out of service and in another part of the pipeline an attack takes place, and the system, the SecureGas architecture, will identify, localize and classify the event. Scenario D, it means a man in the middle, that is to say the attack to the control system, the SCADA, the DCS system. Scenario E deals with the environmental patrol with drone. It means the forecasting and early warning of any geohazard, for example, a landslide caused by rainfall. Scenario F deals with the prescriptive intelligence for recovery. It means SecureGas will provide the best way to recover from any accident. The business case 3 is hosted in ENI infrastructure. We are in North Italy, from Chivasso to Aosta. It is a crude oil pipeline used until 2015. It is 100 meters long, 16 inches of internal diameter. After 2015, it has been inertized and filled with nitrogen at 6 bars. We will use the southern part of the infrastructure for the first 4 scenarios from A to D, and the upper part, the northern part of the pipeline, we will use for scenario E, for forecasting and early warning of geohazards. Here we see EWPMS that I was mentioning before. It is a patented ENI technology for third-party interference and leak detection. Here we see it consists of a multi-point network of vibroacoustic sensors distributed along the pipeline at relative distances of tens of kilometers. The fluid acts as a guide and guide the waves along the pipeline. The sensor will register these acoustic and elastic waves, and in case of interference or leak, will detect, will localize and classify the event, triggering an alarm. The EWPMS interface is shown here. Another ENI technology that will be used in scenario E, the forecasting and early warning of geohazard, is EKMF. EKMF, Cassandra Meteo Forecast, is a ENI technologies for meteo forecasting. It means it is a system for long-term and short-term previsions. Currently, the short-term forecast is used in ENI power combined cycle gas turbines for forecasting the power production. A development of this technology has been done during the years, improving the grid resolution For example, with the Cassandra Alpine model, CALM, with a grid resolution of 5 kilometers. Furthermore, another development has been done for South Italy, CALM HD. It is a 48-hour forecast with 1.3 kilometers of resolution. In business case 3, scenario E, we are developing CALM HD application for Northwest Italy, where the pipeline is located. Here we see also two meteorological stations that have been installed, one in Chivasso, one in Aosta, in order to calibrate the system, the model. So far, business case 3 achieved task 6.2, that is the customization design of the architecture and the business case 3 components. It achieved task 6.3, that means the system and infrastructure adaptation to the business case, and also task 6.4 that has started. For example, in fact, we have installed the ENI EWPMS system and RINA distributed acoustic sensing system. In October 2020, a first field campaign has been performed with these two components in order to register data from tests that are necessary for the system calibration. And currently, the calibration phase has started. As I said before, also two weather stations have been installed for the model calibration. Here in this slide, we see some of the images from the first campaign. In particular, we are dealing with third-party interference tests related to scenario A and scenario C. Third-party interference means any voluntary, malicious, or involuntary intrusion to the pipeline. Here, in particular, we see the intrusion, manual excavation, mechanical excavation, and also direct impact on the pipeline shell with a hammer, with a pendulum, with a shaker. So these tests have been performed in October. Now we move to leak detection test relating to scenario A and scenario C. On a pipe branch, a valve with a nipple has been mounted. The nipple has different shape, different diameters, in order to simulate different type of gas leakage. Here we see two images with a nipple and with an electro valve opening. Then the leak detection test have been performed during a signal tampering to the EWPMS system. This is related to scenario B, signal tampering. It means that this type of leak detection test, has been done during an attack to the component of the EWPMS system. So, concluding, task 6.4 is ongoing, and we are developing and adapting all the extended components and interfaces between the components, and we hope to go on field in March, April 2021 for the final full-scale test and demonstration. Then also task 6.5 will be performed for the evaluation and lesson learned. From this business case, we say that this architecture may be in future, hopefully, implemented in ENI gas assets for improving the asset integrity management in order to secure from any cyber physical attack. The SecureGas will provide the component and also guidelines to enhance the resilience for the critical infrastructure, and also will provide the guidelines for a design to cost and also energy efficiency management of gas infrastructure. Thank you for attention, and feel free to.
Thank you very much, Simone, for the presentation. I remind you, if you have questions, you can write them in the chat. And now I invite the representative of Amber to present the use of extended components in the business case 2 in Lithuania. Vaidotas, the floor is yours. Thank you very much. You can start.
Hello, everyone. I hope you can see my slide.
Yes, we can see and hear you.
Okay. So, unfortunately, our business case is not such, it has not made such progress as other two, but we are hoping to do our best. And since we have a new partner coming to project, and which is essential for our successful project implementation, I hope that in the next year, in the beginning of the next year, we will start working accordingly and we reach our goals. So basically, I will introduce the business case 2 regarding the extended components, what is planned to achieve. So business case 2 is structured into 3 use cases. One is risk assessment of pipeline hub. This one does not include any extended components, so I will not focus on that. Other two are methane leak detection by unmanned aerial vehicle. This is really critical for Amber, for business case owner. And the second one is remote control deployment of valves. So for the use case 2, methane leak detection, it is the objective is the pursuit of efficiency and precision in order to detect methane leakages in the pipeline, especially in the hard to reach areas, forests and fields and others. So the simulation, testing and customization of UAV equipment with detection, inspection and data processing and storage models on selected section of Amber Grid infrastructure will be carried on, and also the blockchain technology will be used for integrity and assurance of data transfer between UAV and the infrastructure of Amber Grid. The key features for this solution are that the drone must fly along the pipeline's route and detect the methane concentration over the pipeline with high sensitivity detector that is based on tunable diode laser absorption spectroscopy method. Each measurement point must be accurately marked with coordinates, points per meter, measurement height captured, photos and other relevant information. Results must be sent to the operator in real-time mode. Also, autonomous flight routed from Argus format layers easily be controlled from a remote location and possibility to switch to manual control. And the system should have the opportunity to integrate data with pipeline integrity management system, PIMS, and other internal information systems. And also, it is planned that system should detect cyber threats and identify high priority threats. Here you can see the basic data flow model for this solution. It will be defined in more detailed ways as we will start working with our new partners. But this is a principal scheme for the data flow. The third use case is remote control deployment of valves. The goal is to verification of a priority list of valves connected to SCADA and development of priority list of not connected valves. This task this task is already completed, and now it is development of multi-criteria decision tool, which contains set of parameters, values, margins, and other values undergoing. And the goal number 2 is to review of the possible risk scenarios where third-party activity could affect the system operations. For example, unauthorized changes to commands or alarm thresholds, or also SCADA software or configuration settings modifications. And we face some challenges during the process that drone data requires integrity checks and solid confirmation that any manipulation has not happened during the process from drone device to analysis tools. That solution is used for scalable signing of the monitoring data directly without any delay. Time of the signing must be comparable, and if data was manipulated, then there must be a proof. So this is the target points for us, and I hope that we will manage to reach our goal. So in short, this is all from business case 2. I hope we will have more information during our next webinars or our events. Thank you.
Thank you very much, Vaidotas, for your presentation. Now, if any one of you has a question or comment now, please feel free to share it in the chat. I will wait a moment. Otherwise, for the external stakeholders, so not the SecureGas partners, I remind you that you can also contact our beneficiaries, our partners through the stakeholder platform. You have their emails indicated there when you log into the stakeholder platform. So you can always ask the questions or share your feedback in private via the stakeholder platform. You can also use the contact form on our website if you wish to contact us with some questions or feedback. I see that at the moment there are no questions or comments from anyone, and no one is typing. So I guess the presentations were quite comprehensive and fully addressed the topic of today. So I guess we can finish as we planned around 11 o'clock. On behalf of the whole consortium and the presenters, I would like to thank all the participants for joining the event. As I said, we recorded the webinar, so it will be soon available on our social media and on our YouTube in particular. As soon as the link is out and uploaded, I will also inform all of you so you can access it freely. So once again, thank you all very much for the presentations and for the participation. And I would like to take this opportunity to also wish you happy Christmas holidays and all the best in the new year. Thank you very much once again. Have a nice day. Goodbye.
Goodbye.
Thank you. Goodbye.
Thank you. Bye-bye.